Okay, in your notebooks you should write a goal today that we're starting a new section on mechanical waves. That's how stuff moves in the universe, from electrons all the way to the universe itself. When we studied thermodynamics, we discovered temperature is a measure of how the atoms and molecules and all that are moving. So this kind of ties into it. Now we're going to do physics, we study motion. We're going to study particular kind of motions today. So on your desk or on your lab table, you should have the new vocabulary sheet. This is going to be due in 2 days. So you have today, tomorrow, and the next day. So this time it's going to be due Friday by 4 o'clock. Remember, take the definitions, the scientific definitions, rewrite them into your own everyday language, and then try to use it in a sentence. Be as close as you can be. This is your introduction to the words. This isn't a test on the words. Please don't leave blanks. Any questions on the vocabulary? This is a long one. Awesome. So let's get into motion. Wait for it to pop up on the screen. So, simple harmonic motion. This is everything Texas State thinks you should learn. You should kind of get a look at it. We're going to do, say, practicing. Our main objectives is going to be understanding what we call periodic motion and simple harmonic motion. Now, you guys know what the word simple means. This is the most basic definition of how stuff moves in a pattern. Harmonic is how frequencies change, how we can build on one frequency and go off another based over a certain time period or some things, like a guitar string. If we pluck different guitar strings, they vibrate at different frequencies, which give us notes. That is a very good idea of simple harmonic motions. If we build on them, we can create new notes. Anyone who's a musician or been in choir know if we play multiple notes together, we sort of create a whole different sound as opposed to that one note. Those are called harmonics. If we take a certain note, we can build off certain areas of harmonics with it. And if we play those notes, it goes. This isn't a music context that I'm talking, but it involves other stuff too. The simplest definition that we first got to work with is periodic motion. The word period means it happens in an interview over and over and over. The periodic chart, we go through stuff. The simplest is our calendars. We talk about a week. A week happens every 7 days. Your birthday happens once a year. The year happens every 365 days. We rotate around the earth. That's a nice period. Periodic motion is a motion, it's moving, that happens over and over again, essentially in the same time. Largely it's round around, back and forth, or similar kind of motions. So we're going to get into those. The most basic one, of course, we always think about our planet. Our planet rotates. Every 24 hours it spins once. Every 365 days it goes around the earth. Really easy way of thinking it. Two important ones that we're going to be dealing with are what we call vibrating motions. These are objects that vibrate on the ends of swings and pendulums. On your desk, feel free to pick it up and play with it. These are kind of cool. You have what we call a wave spring. No, really, feel free to pick them up. And if you hold one end, try not to let it snap together like this one did. If you hold it nice and still, you're going to notice the weight kind of stretches out like a string. If we swing it, try not to bounce it. If you swing it, you get a simple pendulum going back and forth. Early clocks, like the old grandfather clocks, came from that. It's a periodic motion. It kind of covers the same distance. We can use it to set timing. We can get it where that swing happens a certain time. If you're really careful and you kind of let it hang, it hits what we call a neutral position. And if you pull the weight a little bit, you notice from the neutral position it will go the same distance down and the same distance up. We can use that as a measuring period. This is a nice little oscillation one, springs on it. If we know the properties of the spring, we can actually get it where we'll follow a certain time period. Yeah, be careful, it will get hair. I've caught my beard in it before, it's ugly.
So this measures time?
We use it a lot for time. That is one of our first uses, but we can use it for lots of other stuff. If we can calculate the time something happens over it, we can also go back and figure out how long an event's been happening and stuff like that. Also, the different frequencies said different things. I mentioned music is a real easy way to think of it. Guitar strings, they have a different period and a different we think of it as the frequency. Different frequencies are different notes. So that's where we get our different notes, by differentiating. By knowing the time it takes for that period, or the distance it takes for that period, that's how I can tune a guitar string. If I know something's going to vibrate this much, I know it's going to produce that note or that sound. What we're getting onto now is, now that we know what a period is, we're going to talk about the simple harmonic motion. And it's a different kind of case of periodic motion. Usually it's back and forth or up and down. And what it is the object moves from a neutral place. We were just playing with our springs. And on the pendulum, this would be a neutral. I pull it away from the center, and it moves back and forth from center. The resting spot would be center. I pull it down, and it moves up and down from center. That's how we measure simple harmonic motion. Once again, the key word of the day is simple. I love that sound when the spring goes down. As I just showed you with the spring, if we have our center spot, we pull away with it from a pendulum, and it swings, and gravity pulls it back. On our springs, we have our neutral spot. I pull it down, it will go up and down. And if I plot that over time, it looks like our classic sine wave. You see this a lot for frequency and all that, and we'll be playing with that look a lot. It's important because these vibrations on molecular scales are what sets up our sound. I keep referring back to music. The way the string vibrates determines the notes. The way the reed vibrates, if you play a saxophone or an oboe, determines the notes. The way the skin on drum vibrates determines the notes. And when we move along, we're going to get into different atoms. If they vibrate at certain things, we call them different things. Light is the electrons in what we call the electromagnetic spectrum vibrating at certain speed. If they're vibrating in a certain periodic motion, we get blue light, red light, green light. If they're vibrating different, we get gamma rays, X-ray sounds. So the way it vibrates tells us a lot what it is and what it does and how it affects things. You can easily demonstrate it. There's a kind of a cool sign. By the way, this lecture is on the website as a PDF, so all these links work. These links are also in the reading when you do the ebook. Make sure you do that. I should have this already up. You know, with our great computers, you know how links are. This is odd because it's up on my screen. I don't know why it's not up on the... Huh. So it looks like... Okay, dealing with technical difficulties here. Nope, that's not what I want. Yes, we have the world's slowest computers. So the first link kind of shows you a really cool little experiment. We may get into it more later when we have springs, and you can see the effect of hooking different weights on them. It's like a game. And you can pull them different amounts. The kind of cool things to have to them. Believe it or not, later on this stuff will make sense because we can do we can figure out what the gravity and so on for each place is. Let me see if I can get the PowerPoint back. Hey. Awesome. So that was that link. This is kind of a simpler example of that. What we see. We have our motion back, it will plot out. Another form of simple harmonic motions we call uniform circular motion. On your table you have a little tire on an axle. Kind of pick it up and you can see what I'm doing with my big one. Mr. Cook gets the big tire. So I have a little chunk of tape here. And if a tire is spinning or something circular, like our planet going around a thing, from this way we can easily see a circular motion based on it. Right? So kind of look at it from the side. It looks like a circle. That is absolutely nice and easy to go. And it's exactly like simple harmonic motion. Now there's a term that confuses a lot of people called projected motion. Projected is when we throw something, a picture. It's the way we look at it. Now what I'd like you to do is take your wheel and spin it and look at it this way. And if you look at it this way, it no longer looks like a circle. If you had a piece of mark, you're just going to see it coming up and down. It looks linear. Remember, linear means a straight line. That means that is what we talk about in projectile motion. This way it's really obvious we're talking about a circular phenomenon. If we observe it this way, it's not. It's just something that we look coming up and down. But we can still analyze it and get it as the projectile motion. There's kind of a cool video. I'm not going to try to hit that one this time because I got a slide coming up to show you. But keep that in mind. When it's asked in the book about projected motion, it's the way we're viewing the phenomenon. An example is like this. Even if it's a circular motion, or my up and down motion can be, if I'm plotting it, you see this going around in a circular motion, but I can observe it linear going up and down. It will still create the classic sine wave. Same from this. If I was looking down or at a cartwheel, even though I have a circular motion, if I was laying down looking up at it, all I would see is a ball coming here, going that way, coming here, going that way. Can confuse people when they're observing something. They go, no, it's linear motion. No, believe it or not, it's circular motion. So, we're at the end. Yay, guys. So simple harmonic motion, it's a case of what we call periodic motion that repeats itself. Usually moving to a place where we call center. We can demonstrate it with the mass on the spring, with the pendulum, or with a wheel spinning back and forth. Those are the most basic things. And we're going to apply these later onto molecular levels. Remember the words periodic motion, simple harmonic motion? Any questions?
No, sir. No, sir.
Yay! Hey, you guys even answered. Thank you. So,
vocabulary and quiz.
So for today, you have your Unit 9 vocabulary. It has a due date and then the deadline. Remember, I have deadlines now. After a certain date, I won't take them anymore. After 10 days. You have a quick reading, which goes over what I just did on the lecture, and the simple harmonic quiz. A lot of people were not here yesterday. Make sure you go back on the web page. Yesterday, we did a little assignment where you go to a link, and there's a list of physicists. I want you to pick a physicist, and back there, if you didn't get it yesterday, is a worksheet that asks you about their name, what they did, when they were born, if you could ask them a question. I want you to get used to physicists. So please avoid doing Albert Einstein. I got a million of them. That's kind of a lower grade because everybody's lazy and go like, I know Albert Einstein. Try to pick somebody new. There's hundreds of them on that list. Again, any questions? If not, go ahead and start working on vocabulary, simple harmonic motion, any makeup work. Have fun, folks.